Hi, this is Sriram from CSC D section. Topic is Hadmard functions of a inverse matrices. Hadmard matrix. In mathematics, a Hadmard matrix named after the French mathematician Jacques Hadmard is a square matrix whose entires are there plus 1 or minus 1 and whose rows are mutually orthogonal. In geometric terms, this means that each pair of rows in a Hadmard matrix represents two perpendicular vectors, while entires is in exactly half of their columns and mismatched entires in the remaining columns. It is a consequence of this definition that the corresponding properties hold for columns as well as rows. The n-dimensional para- parallelotope spanned by the rows of an n cross n Hadmard parallelotope spanned by vector whose entires are bounded in absolute value by 1. Equivalent, a Hadmard matrix has maximal determinant among matrices with entires of absolute value less than or equal to 1, and so is an extremal solution of Hadmard's maximal determinant problem. Certain Hadmard matrices can almost directly be used as an error correct coding using a Hadmard code generalized in Reed-Muller codes and are also used in balanced repeated replication BRR used by statistics to estimate the variance of a parameter estimator. Next, properties. Let H be a Hadmard matrix of order n. The transpose of H is closely related to its inverse. In fact, where In is the n cross n identity matrix of Ht is the transpose of H. To see that this is true, notice that the rows of H are all orthogonal vectors over the field of real numbers and each have length. Dividing H through by the length gives have length an orthogonal matrix whose transpose in thus its inverse multiplying by the length again gives the equality above as a result. Suppose that M is a complex matrix of order n whose entires are bounded by Mij less than or equal to 1 for each I comma j between 1 and n. Then Hadmard determinant bound states that equality in this bound is attained for a real matrix M if and only if M is Hadmard matrix. The order of Hadmard matrix must be 1, 2 or multiple of 4. Let n be the dimensions of U. Notice that U is a gum if and only if n less than or equal to 2, or every principal submatrix of size 3 is a gum. Since the hypothesis the matrix I plus Tu is a bipotential, it is a diagonally dominant, and we deduce that Uii greater than or equal to Uij by taking t belongs to infinity. This proves the result where n less than or equal to 2. So, in the sequel, we assume n greater than or equal to 3. Consider an principal submatrix of U of size 3 into 3. Since I plus T f of A is a principal of submatrix of I plus T f of U, we deduce that I plus T f of A belongs to BIP. If the result holds for the 3 cross 3 matrices, we deduce that A is gum, implying that U is also a gum. Thus, in what follows, we consider that U is a 3 into 3 matrix that verifies the hypothesis of a theorem. After a suitable permutations where we can further assume that U equals to A B1 B2 C1 D C2 BE, where infinity equals to minimum Uij, I6 equals to J. Take f increasing such that f of infinity f of alpha equals to 0 and f of x greater than 0 for x greater than alpha. Then I plus f of u equals to 1 plus f of a, f of b1, f of b2, f of c1 plus 1 plus f of d 0, f of c2, f of beta 1 plus f of e. Sylvester's construction. Examples of Hadmard matrices were actually first constructed by James Joseph Sylvester in 1867. Let H be the Hadmard matrix of order n, then the Paracharoid matrix is a Hadmard matrix of order 2n. This observation can be applied repeatedly and leads to the following sequences of matrices, also called Walsh matrices. In this manner, Sylvester constructed Hadmard matrices of order 2 to the power of k for every non-negative integer k. Sylvester's matrices have a number of special properties. They are symmetric and when k less than or greater than or equal to 1. 2 to the power of k greater than 1 have trace 0. The elements in the first column and the first row are all positive. The elements in all other rows matrices are closely connected with Walsh functions. Hadmard conjecture. The most important one question in the theory of Hadmard matrices is that of existence. The Hadmard conjecture proposes that a Hadmard matrix of order 4 to the power of k exists for every positive integer k. The Hadmard conjecture has also been attributed to Paley, although it was considered implicit by others priori of Paley's work. A generalization of Sylvester construction proves that are Hadmard matrices of order n and m respectively, then is used to produce Hadmard matrices of higher order. Those of smaller order are known. Sylvester's in 1867 construction yields Hadmard matrices of order 1, 2, 4, 8, 16, 32, etc. Hadmard matrices of order 12 to 20 were subsequently constructed by Hadmard in 1893. In 1933, Raymond Paley discovered the Paley's construction, which produces a Hadmard matrix of order q plus 1, where q is n prime power, that is congruent to 3 module 4, and that produces a Hadmard matrix of order 2 into q plus 1, where q is a prime power, that is congruent to 1 modulo 4. His method uses finite fields. The smallest order that can be constructed by a combination of Sylvester and Paley's methods is 92. A Hadmard matrix of this order was found using a computer of Bureaumeter Colombo and Hall in 1962 at JPL. They used a construction due to Williamson that has yielded many additional orders. Many other methods for construction Hadmard matrices are now known. In 2005, Hadi Khargani and Birzo Taiftar Riaz published their construction of a Hadmard matrix of order 428. As a result, the smallest order for which an Hadmard matrix is presently known is 668. As of 2014, there are 12 multiples of 4 less than or equal to 2000 for which no Hadmard matrix of that order is known. They are 668, 716, 892, 1132, 1244, 1388, 1436, 1676, 1772, 1916, 1948, and 1964. Equivalence and unequivalence. The two Hadmard matrices are considered equivalent if one can be obtained from the other by negating rows or columns or by interchanging rows or columns up to equivalence. There is a unique Hadmard matrix of order 1, 2, 4, 8, and 12. There are 5 inequivalent matrices of order 16, 3 of order 20, 60 of order 22, 24, 4, 87 of order 28. Millions of inequivalent matrices are known for orders 32, 36, and 40 using a Corazar notion of equivalence that also allows transportation. There are 4 inequivalent matrices of order 16, 3 of order 20, 36 of order 24 and 294 of order 28. Hadmard matrices are also unequally recoverable in the following sense. If an Hadmard matrix of order enters randomly deleted, then with overwhelming likelihood one can perfectly recover the original matrix from the damaged one. The algorithm of recover has the same computational cost of matrix inversion. Special cases. Many special cases of Hadmard matrix have been investigated in the mathematical lecturer. Skew Hadmard matrix. A Hadmard matrix is skew if a skew Hadmard matrix remains a skew Hadmard matrix after multiplication of any rows and its corresponding column by -1. This makes it possible, for example, to normalize a skew-Hadmard matrix so that all elements in the first row equal 1. Reed and Brown in 1972 showed that there exists a double molecular tournament of order n if and only if there exists a skew-Hadmard matrix of order n plus 1. In a mathematical tournament of order n, each of n players plays one match against each of the other players, each match resulting in a win for one of the players and loss of for the other. A tournament is regular if each player wins the same number of matches. A regular tournament is doubly regular of distinct players, since each of the n into n minus 1 by 2 matches played result in a win for one of n minus 1 by 2 players defeated by a given player also loses to n minus 3 by 2 other players. The number of player pairs I comma j such that j loses both to I to the given players n minus 1 n minus 3 by 4. The same result should be obtained if the pairs are counted differently. The given player and any of the n-1 other player together defeat the same number of common opponents. This common number was of defeated opponents must therefore by n-3 by 4 a skew Hadmard matrix is obtained by introducing an additional player who defeats all the original players and then forming matrix with rows and columns labeled by players according to the role. That row I and column j contains 1 if I equals to j, or I defeats j and minus 1 if j defeats I. The correspondence in inverse produces a doubly regular tournament for a skew Hadmard matrix. Assuming a skew Hadmard matrix is normalized so that all elements of first row equal 1. Regular Hadmard matrix. Regular Hadmard matrix are real Hadmard matrix whose rows and column sum are all equal. A necessary condition on the existence of regular n into n Hadmard matrix is that n be a perfect square. A circulant matrix is a manifestly regular and therefore a circulant Hadmard matrix would have to be of perfect square order. Moreover, if an n cross n circulant Hadmard matrix existed with n greater than 1, then n would necessarily have to be of the form 4u square with u odd. Circulant Hadmard matrix. The circulant Hadmard matrix conjecture, however, asserts that apart from the known 1 cross 1 and 4 cross 4 examples, no such matrices exist. This was verified by all but 26 values of u less than 10 to the power of 4. Thank you for seeing my video.